Hello everyone, welcome back. Today we enter one of the most puzzling corners of calculus, indeterminate forms. You've probably seen it, dividing 0 by 0. Is it 0? Is it 1? Is it infinity? Well, the truth is, it's none of those. It's indeterminate, meaning uncertain, undefined, and we need better tools to figure it out. Here's the starting point. If the limit of f of x as x tends to c exists, and the limit of g of x as x tends to c also exists, and importantly, the denominator's limit is not 0, then it's straightforward. The limit of f of x over g of x equals the limit of f of x divided by the limit of g of x. In symbols, limit as x approaches c of f of x over g of x equals limit as x approaches c of f of x divided by limit as x approaches c of g of x. That's equation 1 on your screen. But if the denominator tends to 0, then things get tricky. For the ratio to exist finitely, the numerator must also tend to 0. That's when we land in the 0 by 0 form, the first big indeterminate form. And 0 by 0 is not alone. We also get infinity by infinity, infinity minus infinity, 0 times infinity, 0 power 0, infinity power 0, and 1 power infinity. Quite the troublemakers. So remember, 0 over 0 does not mean 0. It means we need to dig deeper. Now let's understand L'Hopital's rule for the 0 by 0 form. Suppose we have two functions f of x and g of x, both differentiable in an interval around x equals c, except possibly at c itself. We also assume that g dash of x is never equal to 0 in that interval. Now, if the limit of f of x as x approaches c is 0, and at the same time the limit of g of x as x approaches c is also 0, then the fraction becomes an indeterminate form of type 0 by 0. In such a situation, L'Hopital's rule tells us that instead of struggling with the original functions, we can take their derivatives. That means the limit of f of x over g of x as x approaches c is equal to the limit of f dash of x over g dash of x, provided this new limit actually exists. This powerful shortcut helps us evaluate otherwise difficult limits. Let's test this with examples. First problem. Limit as x approaches 0 of open bracket x to the power 4 minus 256 close bracket divided by open bracket x squared minus 16 close bracket. Substitute x equals 0. Numerator becomes 0 to the power 4 minus 256. That's negative 256. Denominator is 0 squared minus 16. That's negative 16. So the result is negative 256 divided by negative 16, which equals 16. Nice and clean. But if we tried x equals 4, numerator and denominator would both be 0, the 0 by 0 form. In that case, we factorize. The numerator x to the power 4 minus 256 becomes open bracket x squared minus 16 close bracket times open bracket x squared plus 16 close bracket. Cancel the common factor x squared minus 16, and then the limit can be taken safely. The big idea? Always try substitution or factorization first. Only if that fails do we bring in L'Hopital's rule. Now let's try a deeper one. Evaluate limit as x tends to 0 of open bracket sin x minus x plus 1 over 6 x cubed close bracket divided by x cubed. Substituting directly gives 0 over 0. So let's apply L'Hopital's rule. Differentiate numerator and denominator. First derivative gives cosine x minus 1 plus half x squared over 3x squared. Still 0 over 0. Differentiate again. Numerator becomes negative sin x plus x. Denominator 6x. Still 0 over 0. Differentiate one more time. Numerator is negative cosine x plus 1. Denominator 6. Now substitute x equals 0. Numerator becomes negative 1 plus 1, which is 0. So the limit is 0. Let's move on to mixed cases. First, limit as x tends to 0 of open bracket x minus sine x close bracket divided by open bracket x cubed times sine x close bracket. Numerator expansion, sine x is x minus 1 over 6 x cubed plus higher terms. So x minus sine x becomes x minus open bracket x minus 1 over 6x cubed close bracket, which simplifies to 1 over 6x cubed plus smaller terms. Denominator is x cubed times sine x, which expands as x cubed times x, giving x to the power 4 with corrections. Simplifying, the ratio tends to a constant. Now let's carefully work through a full step-by-step example. We want limit as x tends to 0 of open bracket sine x minus x plus 1 over 6x cubed close bracket divided by x cubed. Given, numerator and denominator both vanish, so this is the 0 by 0 form. Step 1. Differentiate numerator and denominator once. That gives cosine x minus 1 plus half x squared divided by 3x squared, still 0 by 0. Step 2. Differentiate again. Numerator becomes negative sine x plus x, denominator 6x, still 0 by 0. Step 3. Differentiate one more time. Numerator becomes negative cosine x plus 1, denominator 6. Substitute x equals 0, numerator equals 0, denominator equals 6, so final value is 0. And we're done. Repeated application of L'Hopital's rule cracked the puzzle. So, what have we learned today? Indeterminate forms appear in many limit problems, especially the form 0 over 0. Others include infinity over infinity, infinity minus infinity, 0 times infinity, 0 power 0, infinity power 0, and 1 power infinity. We saw that L'Hopital's rule is the main tool. Replace the messy ratio with a ratio of derivatives until the uncertainty disappears. Sometimes algebraic tricks like factorization or trigonometric expansions work faster. Through ISC examples, we solved algebraic, trigonometric, and exponential cases, and even saw how repeated differentiation may be necessary. So, the final takeaway: indeterminate does not mean impossible. It means we need smarter tools. And with L'Hopital's rule and algebraic insight, we can resolve these tricky limits. That's it for today's class. In the next session, we'll explore even more calculus adventures. Until then, keep practicing and remember, 0 by 0 is not the end. It's just the beginning of deeper math.